For centuries, humans have gazed up at the night sky in wonder, contemplating the vastness and beauty of the universe. With the development of astronomy and cosmology, we have learned more about the universe than ever before, including the remarkable discovery that our universe is expanding. But as we continue to explore the cosmos, we are left with daunting questions. If you keep traveling through space in an imaginary faster-than-light spaceship, would you ever arrive at some boundary, unable to go any further? If yes, what lies beyond it? And if there is more beyond our universe, what could it be like? It's all very hard to imagine. Then again, an infinite universe is just as difficult to wrap your head around. After all, there must be something that space is expanding into, right? Let's start with a related but easier to grasp concept. Our universe has an edge, not in space, but in time. Because the hot Big Bang occurred at a known, finite time in the past, 13.8 billion years ago, with an uncertainty of less than 1%. There's an edge to how far away we can see. Even at the speed of light, the ultimate cosmic speed limit, there's a fundamental limit to how far back we can see. The farther away we look, the farther back in time we're able to see. Here's what we see as we approach the edge of the universe. Today, we see the universe as it exists, 13.8 billion years after the hot Big Bang. Most of the galaxies we see are clumped together in galactic groups, like the Local Group, and rich clusters, like the Virgo cluster, separated by enormous regions of mostly empty space known as cosmic voids. The galaxies within these groups are a mix of spirals and ellipticals, where a typical Milky Way-like galaxy forms an average of about one new sun-like star per year. In addition, the normal matter in the universe is mostly made of hydrogen and helium, but about 1 to 2% of the normal matter is made of heavier elements from the periodic table, enabling the formation of rocky planets like Earth and complex, even organic chemistry. While there's lots of variety, some galaxies are actively forming stars, some have active black holes, some haven't formed any new stars for billions of years, etc. The galaxies we see are large, evolved, and clumped together, on average. But as we look farther and farther away, we start to see how the universe grew up to become this way. As we look to greater distances, we find that the universe is slightly less clumpy and slightly more uniform, particularly on larger scales. We see that galaxies are lower in mass and less evolved. There are more spirals and fewer elliptical galaxies. On average, there are greater proportions of bluer stars, and the star formation rate was higher in the past. There's less space between galaxies on average, but the overall masses of groups and clusters is smaller at earlier times. It paints a picture of a universe where today's modern galaxies were created by smaller, lower-mass galaxies merging together over cosmic timescales, building themselves up to become the modern-day behemoths we see all around us. The universe, at earlier times, consists of galaxies that are physically smaller, lower in mass, closer together, larger in number, bluer in color, richer in gas, with higher rates of star formation and with fewer proportions of heavier elements as compared to today's galaxies. But as we go farther and farther away, to earlier and earlier times, this gradually changing picture begins to transform abruptly. When we look back to a distance that's presently 19 billion light-years away, corresponding to when only 3 billion years had passed since the hot Big Bang, we see that the universe's star formation reached its maximum, about 20-30 times the rate at which new stars are formed today. An enormous fraction of supermassive black holes are active at this time, emitting enormous amounts of particles and radiation due to the consumption of surrounding matter. For the past 11 billion years or so, the universe's evolution has been slowing down. Sure, gravitation continues to collapse structures, but dark energy begins to work against it, coming to dominate the universe's expansion more than 6 billion years ago. New stars continue to form, but the peak of star formation is in our distant past, and supermassive black holes continue to grow, but shone at their brightest earlier on. with a greater fraction of them fainter and inactive today than during these early stages. As we go to greater and greater distances, closer to the edge defined by the start of the hot Big Bang, we start to see even more significant changes. When we look back to distances of 19 billion light-years, that corresponds to a time when the universe was just 3 billion years old. Star formation was at its peak, and the universe was maybe 0.3 to 0.5% heavy elements. But as we close in on 27 billion light-years away, the universe was only 1 billion years old. Star formation was much smaller, as new stars formed at rates approximately a quarter of what they'll be, later on, at their peak. The percentage of the normal matter that's made of heavy elements plummets precipitously, to 0.1% at an age of 1 billion years, and to just 0.01% at an age of around 500 million years. Rocky planets, in these early environments, may well have been impossible. Not only was the cosmic microwave background significantly hotter, it would have been at infrared rather than microwave wavelengths. But every galaxy in the universe should be young and full of young stars. There are likely no elliptical galaxies this early on. Going farther back than this really pushes the limits of our current instrumentation, but telescopes like Keck, Spitzer, and Hubble began to take us there starting in the 1990s. Once we go back to distances of approximately 29 billion light-years or farther, corresponding to times where the universe was 700, 800 million years old, we start to run into the first edge of the universe, the edge of transparency. We take for granted today that space is transparent to visible light, but that's only true because it isn't full of light-blocking material, like dust or neutral gas. But at early times, before enough stars had formed, the universe was full of neutral gas and hadn't become fully ionized by the ultraviolet radiation from these stars. As a result, a lot of the light we see is obscured by these neutral atoms, and it's only once enough stars have formed that the universe becomes fully reionized. This is, in part, why infrared telescopes, such as NASA's flagship mission, the James Webb Space Telescope, are so crucial to investigating the early universe. There's an edge to where we can see in the wavelengths we're familiar with. At distances of 31 billion light-years, corresponding to a time of just 550 million years after the Big Bang, we reach the edge of what we call reionization, where the majority of the universe is mostly transparent to optical light. Reionization is a gradual process and takes place unevenly. It's like a jagged, porous wall in a lot of ways. Some places see this reionization happen earlier, which is how Hubble spotted its most distant galaxy ever, at 32 billion light-years away, just 407 million years after the Big Bang. But other regions remain partially neutral until nearly 1 billion years have passed. James Webb has now taken us even farther, showing us galaxies as far back as 290 million years after the Big Bang, where they still appear large, evolved, and are not quite pristine in terms of the elements that are present within them. There must still be stars and galaxies out there beyond even what James Webb has shown us so far. Beyond those limits of what our current telescopes can see, however, we can still measure the indirect signs that stars have formed. Through the emission of light from hydrogen atoms themselves, which only occurs when stars form, ionization occurs, and then the free electrons recombine with the ionized nuclei, emitting light in the aftermath of that. Right now, we only have the indirect signatures of this signature of early star formation, although there are many that dispute the validity of this signal, indicating that young galaxies existed as early as 180, 260 million years after the Big Bang. These proto-galaxies formed enough stars that we can see the first hints of their existence buried in the data, corresponding to a distance of between 34 and 36 billion light-years away. Although our current telescopes haven't seen these galaxies directly, the great expectation of many astronomers is that a long enough deep field exposure with James Webb will reveal them. However, there are likely still sources of light, and the first ionized regions of space in the universe, going back even before that. The very first stars of all, in the rare regions that grow in mass density the fastest, are expected to come about between 38 and 40 billion light-years away, corresponding to times just 50 to 100 million years after the Big Bang. Before that, the universe was only dark, full of neutral atoms, and radiation from the Big Bang's leftover glow. Going back even farther, we fully expect there to be additional edges of interest. 44 billion light-years away, the radiation from the Big Bang was so hot that it becomes visible. If a human eye were to exist, it would be able to see that radiation begin to glow red, similar to a red-hot surface. This corresponds to a time just 3 million years after the Big Bang. If we go back to 45.4 billion light-years away, we come to a time just 380,000 years after the Big Bang, where it becomes too hot to stably maintain neutral atoms. This is where the leftover glow from the Big Bang, the cosmic microwave background, originates from. If you've ever seen that famous picture of the hot and cold spots from the Planck satellite, this is where that radiation originates. And before that, 46 billion light-years away, we come to the earliest stages of all, the ultra-energetic state of the hot Big Bang, where the first atomic nuclei, protons and neutrons, and even the first stable forms of matter were created. At these stages, everything can only be described as cosmic, primordial soup, where every particle and antiparticle in existence can be created from pure energy. But what lies beyond our observable universe? Is there an abyss of nothingness beyond the light signals that could possibly reach us since the Big Bang? Is there just more universe like our own out there past our observational limits? Or is there a multiverse, mysterious in nature and forever unable to be seen? In fact, scientists believe that unless there's something seriously wrong with our understanding of the universe, the multiverse must be the answer. But why is that? To understand the real reason behind it, let's first review everything you need to know about the multiverse. The multiverse, at its core, is a very simple concept. Just as the Earth doesn't occupy a special position in the universe, nor does the Sun, the Milky Way, or any other location, the multiverse goes a step farther and claims that there's nothing special about the entire visible universe. The multiverse is the idea that our universe, and all that's contained within it, is just one small part of a larger structure. This larger entity encapsulates our observable universe as a small part of a larger universe that extends beyond the limits of our observations. That entire structure, the unobservable universe, may itself be part of a larger space-time that includes many other disconnected universes, which may or may not be similar to the universe we inhabit. If this is the idea of the multiverse, I can understand your skepticism at the notion that we could somehow know whether it does or doesn't exist. After all, physics and astronomy are sciences that rely on measurable, experimental, or otherwise observational confirmation. If we are looking for evidence of something that exists outside of our visible universe and leaves no trace within it, it seems that the idea of a multiverse is fundamentally untestable. But there are all sorts of things that we cannot observe that we know must be true. Decades before we directly detected gravitational waves, we knew that they must exist because we observed their effects. Binary pulsars, spinning neutron stars orbiting around one another, were observed to have their revolutionary periods shorten. Something must be carrying energy away, and that thing was consistent with the predictions of gravitational waves. While we certainly welcomed the confirmation that LIGO and Virgo provided for gravitational waves via direct detection, we already knew that they needed to exist because of this indirect evidence. Those who would argue that indirect evidence is no indicator of gravitational waves might still be unconvinced that binary pulsars emit them. LIGO and Virgo didn't see the gravitational waves that came from the binary pulsars we've observed. So if we cannot observe the multiverse directly, what indirect evidence do we have for its existence? How do we know that there's more unobservable universe beyond the part we can observe? And how do we know that what we call our universe is likely just one of many embedded in the multiverse? We look to the universe itself and draw conclusions about its nature based on what observations about it reveal. When we look out to the edge of the observable universe, we find that the light rays emitted from the earliest times, from the cosmic microwave background, make particular patterns on the sky. These patterns not only reveal the density and temperature fluctuations that the universe was born with, as well as the matter and energy composition of the universe, but also the geometry of space itself. We can conclude from this that space isn't positively curved, like a sphere, or negatively curved, like a saddle, but rather spatially flat, indicating that the unobservable universe likely extends far beyond the part we can access. It never curves back on itself, it never repeats, and it has no empty gaps in it. If it is curved, it has a diameter that's hundreds of times greater than the part we can see. With every second that ticks by, more universe, just like our own, is revealed to us, consistent with this picture. That might indicate that there's more unobservable universe beyond the part of our universe we can access, but it doesn't prove it, and it doesn't provide evidence for a multiverse. However, there are two concepts in physics that have been established far beyond a reasonable doubt: cosmic inflation and quantum physics. Cosmic inflation is the theory that gave rise to the hot Big Bang. Rather than beginning with a singularity, there's a physical limit to how hot and how dense the initial early stages of our expanding universe could have reached. If we had achieved arbitrarily high temperatures in the past, there would be clear signatures that aren't there. Large amplitude temperature fluctuations early on, seed density fluctuations limited by the scale of the cosmic horizon, and leftover high-energy relics from early times, like magnetic monopoles. These signatures are all missing. The temperature fluctuations are at the 0.03% level. The density fluctuations exceed the scale of the cosmic horizon. The limits on monopoles and other relics are incredibly stringent. The fact that these signatures aren't there have an enormous implication to them. The universe never reached those arbitrarily high temperatures. Something else came before the hot Big Bang to set it up. That's where cosmic inflation comes in. Theorized in the early 1980s, it was designed to solve a number of puzzles with the Big Bang, but did what you'd hope for any new physical theory. It made measurable, testable predictions for observable signatures that would appear within our universe. We see the predicted lack of spatial curvature. We see an adiabatic nature to the fluctuations the universe was born with. We've detected a spectrum and magnitude of initial fluctuations that jibe with inflation's predictions. We've seen the superhorizon fluctuations that inflation predicts must arise. We may not know everything about inflation, but we do have a very strong suite of evidence that supports a period in the early universe where it occurred. It set up and gave rise to the Big Bang, and predicts a set and spectrum of fluctuations that gave rise to the seeds of structure that grew into the cosmic web we observe today. Only inflation, as far as we know, gives us predictions for our universe that match what we observe. So, big deal, you might say. You took a small region of space, you allowed inflation to expand it to some very large volume, and our observable visible universe is contained within that volume. Even if this is all right, this only tells us that our unobservable universe extends far beyond the visible part. You haven't established the multiverse at all. And all of that would be correct. But remember, there's one more ingredient we need to add in: quantum physics. Inflation is treated as a field, like all the quanta we know of in the universe, obeying the rules of quantum field theory. In the quantum universe, there are many counterintuitive rules that are obeyed, but the most relevant one for our purposes is the rule governing quantum uncertainty. While we conventionally view uncertainty as mutually occurring between two variables, momentum and position, energy and time, angular momentum of mutually perpendicular directions, etc., there's also an inherent uncertainty in the value of a quantum field. As time marches forward, A field value that was definitive at an earlier time now has a less certain value. You can only ascribe probabilities to it. In other words, the value of any quantum field spreads out over time. Now, let's combine this. We have an inflating universe on one hand, and quantum physics on the other. We can picture inflation as a ball rolling very slowly on top of a flat hill. So long as the ball remains atop the hill, inflation continues. When the ball reaches the end of the flat part, however, it rolls down into the valley below, which converts the energy from the inflationary field itself into matter and energy. This conversion signifies the end of cosmic inflation through a process known as reheating, and it gives rise to the hot Big Bang we're all familiar with. But here's the thing. When your universe inflates, the value of the field changes slowly. In different inflating regions, the field value spreads out by randomly different amounts and in different directions. In some regions, inflation ends quickly. In others, it ends more slowly. This is the key point that tells us why a multiverse is inevitable. Where inflation ends right away, we get a hot Big Bang and a large universe, where a small part of it might be similar to our own observable universe. But there are other regions, outside of the region where it ends, where inflation continues for longer. Where the quantum spreading occurs in just the right fashion, inflation might end there too, giving rise to a hot Big Bang and an even larger universe, where a small portion might be similar to our observable universe. But the other regions aren't still just inflating, they're also growing. You can calculate the rate at which the inflating regions grow and compare them to the rate at which new universes form and hot Big Bangs occur. In all cases where inflation gives you predictions that match the observed universe, we grow new universes and newly inflating regions faster than inflation can come to an end. This picture of huge universes, far bigger than the meager part that's observable to us, constantly being created across this exponentially inflating space, is what the multiverse is all about. It's not a new, testable scientific prediction, but rather a theoretical consequence that's unavoidable, based on the laws of physics as they're understood today. Whether the laws of physics are identical to our own in those other universes is unknown. If you have an inflationary universe that's governed by quantum physics, a multiverse is unavoidable. As always, we are collecting as much new, compelling evidence as we can on a continuous basis to better understand the entire cosmos. It may turn out that inflation is wrong, that quantum physics is wrong, or that applying these rules the way we do has some fundamental flaw. But so far, everything adds up. Unless we've got something wrong, the multiverse is inevitable, and the universe we inhabit is just a minuscule part of it. That begs the question, if there are other universes, can we ever visit them? Numerous popular movies are playing with that idea, including Everything Everywhere All at Once, Doctor Strange and the Multiverse of Madness, Loki, Spider-Man, No Way Home, and others going back decades. But they always have some handy device for multiverse travel that physicists lack. A magician's incantation, say, or a quantum Bluetooth device. Real physicists haven't altogether worked out how we'd encounter other universes, but the answer partly depends on what kind of multiverse you're talking about. If we live in the many worlds universe, we create new worlds or universes all the time. Every time we make a decision or choose a particular path, some version of us simultaneously chooses an alternate path, or possibly several others, depending on how many possible paths there are. So, if you decided to date someone, some version of you decided not to, and that version split off into a different timeline. Later, if you decide to marry your significant other, another version of you will decide not to, and another you is created. This idea originated with Erwin Schrödinger's equation on quantum wave function, which explains that a particle exists in a superposition, or wave of possibilities, until it is measured, at which point the wave collapses, leaving a single particle in a specific location. Unfortunately, no one has ever been able to explain why it collapses. American physicist Hugh Everett, who posited the many worlds interpretation of the wave function in 1955, said that, in fact, the wave doesn't collapse. Instead, all the probabilities happen, but you will only be aware of the one you experience. The others will branch off into different timelines. And since the whole universe exists as part of a single superposition probability wave, the universe splits itself into new timelines all the time. Loki and Everything Everywhere All at Once seem to have borrowed from this notion. In Loki, decisions that created new timelines were deemed variants of the sacred timeline and pruned, so that only one reality would prevail. In Everything Everywhere, the characters jump into other timelines by doing wild stuff, like stapling their foreheads. Such choices, deliberately abnormal for their own lives, would help them get to other universes. They also had a nifty Bluetooth device. Today, if we're creating new timelines, physicists like Sean Carroll say, we'll never know or experience them. But avid many-worlds theorist David Deutsch hopes that a mature quantum computer would be able to detect and record the divergence. He also believes we'll one day be able to upload ourselves into quantum computers, so maybe we'll be able to see how our other selves fared. Other multiverse theories postulate universes that exist in our timeline. They're just too far away for us to see. These are suggested by the math in string theory, or the eternal inflation theory, which states that the multiverse is expanding forever and creating new bubble universes. But they're so far away, we are unlikely to encounter them. They might be membranes or brains floating in space, each defined by a set of extra dimensions. Or they might be infinite probability bubbles formed by the inflationary stretch of space and time, called quantum foam or space foam, creating a quantum spacetime. Each bubble could expand into a universe. Some theories propose that the different laws of physics in these universes would cause them to collapse without creating stars, or that humans could never survive there. Others say that if there are an infinite number of these universes, some of them would have identical physical laws to ours, in the same way that a couple who produced infinite children would wind up with at least two with the same gene combination. Interacting with these universes presents a conundrum, though. It would be cool if they gently bumped into one another. Imagine that, walking down the street, you were suddenly confronted with an alternate universe where the supermarket used to be. But that seems unlikely, as physicists predict that two bubble universes colliding would be a violent event, and may even be the source of the Big Bang. Another way to get from one universe to another would be a wormhole, a tunnel comprised of two connected black holes where an incredibly dense mass has pulled space-time into the shape of a funnel. Connect two, and you can travel great distances quickly, kind of like going through a tunnel in a mountain, rather than going over or around it. Lots of movies play with wormholes, including Interstellar and Contact. Einstein's theory of general relativity predicts the possibility that a black hole, instead of ending in the crushing destruction of the gravity of a singularity, would actually funnel quantum information through to a white hole at the other end. He called these Einstein-Rosen bridges. A white hole has been described as a black hole running backward in time. It spews matter out as wormholes suck them in. So far, no white holes have been observed, but scientists are still looking. One theory suggests we have a mirror or bizarro universe running backward in time, connected to our universe. There's also a theory that quantum entanglement could connect two ends of a black hole into a wormhole. But even without wormholes, there are other possible modes of travel to get us to other universes. One day, we may discover a dimension that cuts across space-time. Or a future generation or more advanced being could invent faster-than-light travel which, barring a wormhole, would be needed to span the extraordinary distances between these universes. In the meantime, it's fun to imagine what you might be up to out there. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.